now that we have the addition of our last panelist, I think we are ready to go. And I was just reminded by our panelists that we tried to do something a little different here this time. And instead of saving all of our questions to the end, we're going to have a few questions after each presentation. And then a panel discussion at the end. So a little bit of change to our normal program, which is always interesting. And I'm hoping that we find this different format to be useful. So also, as a reminder, we can always have your questions put in the Q&A chat box at the bottom of the screen. You can see it down at the bottom. So if any question comes up at any time, just put it in the chat box. I'm going to ask my panelists to keep an eye on the chat box themselves. So if there's a quick question you have comes up, they can answer it for you right away. Boom, click, and it's done. And that'll be really helpful. So, okay. So I want to welcome everyone to the International Water Resources Association webinar on groundwater success stories, large-scale water transfer and managed aquifers. We really thank you all for joining us here today. We have a number of panelists and we have a couple of moderators. So I'm going to introduce everyone here. We have Lili Yu, a professor at the General Institute of Water Resources and Hydropower Planning and Design at the Ministry of Water Resources in China. Kathryn Sorensen, Director of Research and Professor of Practice at the Kyle Center of Water Policy at the Morrison Institute for the Arizona State University in Arizona. I believe it's quite early for you, so thank you for joining us. Bogadi Mathangwane, Deputy Director, Department of Water Resources, Water Affairs in Botswana, and Tefo Lobalo, Regional Manager, Department of Water Affairs in Botswana, and Kelly Gaboiphiwe, Hydrologist, Department of Water and Sanitation in Botswana, and Yan Yang, Senior Engineer at the General Institute of Water Resources, Hydropower Planning and Design at the Ministry of Water Resources of China. We also have moderating Karen Wilhelm, the Principal Researcher at the International Water Management Institute and Coordinator in South Africa, and Tibor Strigley, Associate Professor at IHE Delft Institute of Water Education in UNESCO. So, as you also know, after all those acronyms, this is a webinar hosted by the International Water Resources Association, and the IWRA is an international network of researchers and practitioners who work on a multidisciplinary range of water resource issues. We provide a global knowledge-based forum for bridging disciplines and geographies by connecting professionals, students, individuals, corporations, institutions, everyone who's concerned with the sustainable use of the world's water resources. So this webinar, just so you know, will focus on 3 different case studies. So we're bringing together Africa, Asia, and North America to help us better understand the unique conditions and the trajectories under which each of these areas have developed, and then kind of the institutional framework surrounding them. Like I said, we're focusing here so often the groundwater issues get framed as sort of a negative. They're running out, they're running dry, we're not managing them well. But there's a lot of success stories in there as well. So the purpose of this event, which is coming to you from the Groundwater Task Force of the IWRA, is to focus on the success, look on the positives, and find out what kind of messages and techniques have worked elsewhere, and then we can apply it to perhaps your case study or perhaps for you. So that's kind of the thinking and the genesis behind this series of webinars from our Groundwater Task Force. Now, just to kind of go over the quick format, as I mentioned, was a little bit different this time. What we're going to do is start with a short presentation here from one of our moderators, Karen, and then we'll be doing each of the case studies with short clarifying questions coming up afterwards. And then we'll have a panel discussion at the end. So like I said, please, if you have any questions that come up, put them in the chat box right away, and then we'll address them when it comes time for that. And similarly, just as a reminder, we'll have the recordings up on the internet, www.iwra.org, as well as having any PowerPoint slides up there as well. Just give us a couple days, we'll get that taken care of. So with all of that in mind, please let me just turn the floor over to our moderator, Karen Wilhelm.
Okay.
Perfect.
Thank you so much, Scott, for the introduction. And thank you to all our attendees. And thank you to all our panelists and speakers and moderators and introducers and everybody on board. Thank you for joining us and spending time with us today. It's really great to have this opportunity to dig into this topic, which sort of came to mind as something that maybe not has been so much covered, at least not at the global scale, maybe more, you know, from case to case from scheme to scheme, because this is not a new technology that we're discussing here today, but trying to look across and share lessons and see what is the status and what are some of the key similarities, what are some of the key differences when we look across major schemes in the world. So yeah, I just put here the introductory slide. So we're talking about large-scale water transfer combined with managed aquifer recharge. And as Scott already mentioned, we'll be talking about 3 different schemes. So we have one from China, and we have one from the US, and we have one from Southern Africa, from Botswana. Some of them are transboundary, either in an international sense or more in a within a national boundary. You can also have sort of transboundary issues. But let me just move on, and not to take too much time. I'm basically going to give a very brief introduction to the topic, and then I'll hand over to the 3 speakers that will be presenting the various cases, and then we will have an open panel afterwards. I will be moderating, but we also have Tefo from IWRA to help us with the chat box. So please feel free to put any questions in the chat box. I should also mention, and I think Scott forgot to say that, but this is also a webinar organized by GIWP, so the Groundwater Solutions Initiative for Policy and Practice, which I'm coordinating. It's a global initiative of about 30 international partners working in groundwater for development, seeing how we can collaborate to improve sustainability of groundwater, as it's becoming very high on the agenda as water stress is increasing. And it's also important to say that this webinar celebrates the Year of Groundwater. 2022 is a UN Year of Groundwater, and so this webinar is a webinar in a series, and the first year this year, and there will likely be more this year. So stay tuned to this webinar series and see what's otherwise coming up. So here we have our speakers. They were already mentioned, and I will not spend too much time further on it. And I would encourage everybody to introduce themselves. So I'm Kathryn Wilhelm. I'm a principal researcher with IMI, and I've been working on groundwater for 20-30 years. And now I think it's all clear that we have a world which is on its edge, creating a lot of difficulties for development as the populations grow, as we have more urbanization, we have climate change, which basically creates long periods of droughts interspersed with periods of flooding. This is kind of the scenario that we are headed towards, while we have socioeconomic development, but being hampered by these natural causes. And as I think everyone is clear that the water sector is heavily affected by climate change, and on the other hand, the climate sector is where we can try to do a lot to adapt and to cope with climate change. And this is exactly where this topic comes in, the issue of how can we increase our water buffer, our water storage, and how to do that smarter maybe than what we have done previously. So previously we have talked about dams, increasing the dam storage, and we have talked about large-scale water transfers to equilibrate geographic disparity between, wet and dry areas. Now we are increasingly coming to the point where we see that we need to also bring in the aspect of the subsurface as a component of the storage space, because the groundwater and the surface space provides some added advantages in terms of storing water, in terms of minimizing the evaporation losses, and also oftentimes the water footprint that comes with a large dam is sort of not relevant once you get the water underground and you store it there. So there are definitely advantages for this kind of solutions in the kind of scenario that we're looking at today. Again, the world on its edge, and oftentimes we forget about groundwater, and that's why I put it really here front and center to say that this is something that we need to put much more attention to as we go forward. and see groundwater and the subsurface space, the aquifers, as part of the solution space for climate adaptation and for adaptation more broadly. And this can be done in many ways, but it has to be done in an evidence-based way, has to be done in an informed way and a participatory way, and all the things that make it sustainable. And I'm sure the speakers will testimony to that a lot. So we will see more examples of that as we go. Now, just to say, you can see on the left, the large water transfer schemes. And on the right side, you can see, to start with here, in the upper corner, the dams that are often being used to store some of the transferred water after it's being used. There could even be dams on the way as part of the transfer schemes. But now we're looking sort of at the situation here, where we're now having the end station, if you like, being the subsurface. And as I said, that has some added advantages. We're also looking at saving as much water as possible. So we sometimes also see the opposite direction, where we're actually pumping water out of the ground and creating large transfer schemes that go from an aquifer to a dam or to a city or whatever. We're not going to talk about that today, but just keep that in mind as well. That's also kind of an option and a solution that has been used. But I think we all agree that it makes more sense to try to put it underground as part of the storage scheme. And then bridge some of our drought periods. Now, basically, talking about where we have transfer schemes today. So you can see here a global map where we have existing, what they call mega projects, transfer projects. And the most stunning thing from this paper in 2018 is actually what they map in terms of the future water transfer schemes. And you can see there's a huge difference from what we have today and what is being envisaged for the future. And those are all the green schemes that you can see here. And it's quite obvious that a lot of the water is now being transferred from the more humid areas to the arid areas. And there's no, that's a no-brainer. But then the question is, how do we do that optimally and most effectively and efficiently? And I just encircled here the three cases that we'll be discussing today. So you can see California there to the left, Botswana, Southern Africa. There's already a lot of transfer schemes there, especially in South Africa, but not much being combined with managed aquifer recharge. So this is kind of a novel approach in Southern Africa today. And then China, we have the south to north water transfer scheme, which is the biggest of them all, actually. I don't think I'll go into this. I think I already mentioned it. So I think in the sake of saving time, I will already now hand over to the first speaker. And this will be our colleague from China. I think it's Yan Yang. Are we able to go on this? Please feel free to come in. This is just kind of a commercial for a book that we have done recently on managed aquifer recharge, covering 28 cases across the globe, including also the US case. So I'll hand over. Thanks, Scott and Tibor.
Scott, you're muted, but I think we can move on, right?
Yes, yes, please.
So let's go direct to my presentation. Hello, everyone. Good afternoon. I'm very glad to be the first to share with you some of the experiences gathered from the MAR work in China for the past few years. My presentation is composed of 5 parts. The first is the overview. And today I will focus the study area on the MAR in North China Plain. I suppose some of you may have already been very familiar with this place. It is the hot spot for groundwater study, especially in the study of the groundwater overexploitation elevation. But I still want to give a brief introduction on this area. North China Plain locates in the very heart of China with very large area of very good farmland. It is the second largest plain in China, covering 5 provinces, including Beijing, Tianjin, Hebei, Henan, and Shandong, with 1 out of 10 of the total population and 20% of total GDP of China. In the meantime, North China Plain has very limited water resources, with about 400 cubic meter per capita per year, and groundwater resources take a very large ratio in the total water resources, and 46% of the water supply came from groundwater, and 61% of groundwater was consumed for agricultural use. So groundwater played a very important role in this area. For the past decades, North China Plain suffered severe groundwater overexploitation problem. The overexploited area was over 254,000 square kilometers. The overpumped rate was over 6 billion cubic meter per year. We can see from the picture that the overexploited area covered more than 15% of the plain. Besides, the water consumption is very high, reached 80 billion cubic meters at the peak. So leaving almost no space for the ecological water use. And the river flow to the sea has been significantly reduced. The rivers and the lakes in North China Plain suffers even worse problem. Ecological functions of rivers and lakes were severely damaged. The occurrence of the river dry out reached 32 out of 55 in High River Basin since the 1980s. The average annual days and the total length of the river dry out reached 166 days and 781 kilometers, respectively. And the covering area of rivers and lakes has been seriously reduced. And the wetland areas of Baiyang Dian River, Hengshui River, and other major lakes have been reduced by 30% compared to the 1950s. We think before taking some actions to be taken, summarizing the main concerns is very important to guide the following actions. Here we have 4 main concerns based on the key issues I have introduced. The first is the restoration of river morphology. The second is ecological flow increase to a reasonable level. The third is the restoration of groundwater level, which means we hope to see the rise of the groundwater level. The last concern is restoration of ecological functions, which also means the maintenance of the wetland areas. So we could say that the reduction of the groundwater abstraction is very vital to alleviate the degradation of the water system. And we have already done a lot on that, on the groundwater, on the reduction of groundwater abstraction. But this is another story of that. So beside that, the MAR also came into our mind. The dry out rivers and lakes leave huge space and become a very ideal place for MAR. MAR, we think, could solve the groundwater degradation problem from another way. Next, I want to briefly introduce the South to North water transfer project. Actually, it is the most important water source for MAR in North China Plain. It was put into operation in 2014. North China Plain is the main target area of the project, but Because of the delay of the matching water supply network, it makes the transferred water cannot be consumed as planned. So this part of water became a very ideal water source for the MAR. Next, I want to introduce the pilot area of the MAR. The MAR was conducted to 3 rivers in North China Plain, which were the Hutuo River, this place, Fuyang River and the South Juma River from the September 2018 to September 2019. There are mainly 2 water sources, which are the south to north water transfer project and the upstream reservoirs. And the total recharge rate reached 1.3 billion cubic meters. And it should be noted that from the year of 2019, the MAR has become a regular work each year in North China Plain. And I will introduce that next slide. And we could notice that in the picture that there were not only the SMWTP and upstream reservoirs as the water sources, and more water transfer projects were involved. But in today's presentation, I will focus on the 2018 to 2019, this period. And I still want to introduce the 2020 MAR work. In 2020, the Yellow River, Luan River, and reclaimed water are introduced as a vital water source, and up to 22 rivers get recharged, and the total recharge rate reached 4.4 billion cubic meters. Some of the river even flowed to the sea. And in 2021, the recharge rate reached 2.8 billion cubic meters. We have not got the actual data because the year just passed. And one extra MAR was conducted just before the flood season in 2021 summer, because we think to make our full use of the discharge water from the upstream reservoir, it is a good time to conduct the MAR. Next, I want to introduce the 3 pilot rivers state just before the MAR. The first is the Hutuo River. Its river channel was totally dry and severely damaged, with garbage dumped, and the river bank is widely distributed with cultivated land. The second is the Fuyang River. Its river channel was well maintained, but with garbage dumped at some parts. The third is the South Juma River. It was damaged with garbage dumped. Here in this table, we could see that the information on overexploited rate, groundwater deaths, and the length of dry out of the 3 pilot river has been gathered before the scheme was formulated. So the next part, I will introduce the scheme of the MIR. Based on the general information of North China Plain, the state of the pilot river, we could easily develop the scheme of the MIR. The first is the targets of MIR. 5 concrete targets were set here. The first is the increase the area of lakes and wetland could reach 27 to 37 square kilometers. The second is increase the area of lakes and wetland could reach the groundwater level along the recharge river were expected to have a general rise, and the river ecological flow and could increase to the reasonable level. And the last target is the restoration of the water morphology and ecological function. Then we developed three main tasks based on the targets. The first is the river recharge. Through the multi-source water deployment and effective institutional arrangement. The second task is the river channel cleanup to facilitate the water infiltration. The third task is the dynamic monitoring and evaluation so as to track the implementation process of the MAR. For the third part, I want to introduce the detailed implementation task of the three tasks of the institution and the corresponding institution arrangement of the MAR. As for the river recharge, over 1.3 billion cubic meter of water from multi-source was recharged, in which 870 million came from the middle route of SNWTP, 370 million from the local reservoirs, and very little, which is 1.8 billion from the reclaimed water. And the three pictures are the river bed after the MAR, the three pilot rivers. We could imagine that before MAR, these river beds were almost dry. And for the river cleanup task, more than 1 million cubic meter of dumped trash was cleaned. By cleaning up the riverbed, the appearance of the river was obviously improved and provides the condition, a good condition for implementing the water recharge. These two pictures show the river state before and after MAR. We think the cleanup of the recharge site is a quite necessary part of MAR.
Another 1 minute.
Oh, only 1 minute. Sorry.
1.5.
And the third task is the dynamic monitoring and evaluation. We have the recharge monitoring, groundwater level and quality monitoring, and influential area monitoring, precipitation effect evaluation, and the water cover area assessment. All of these are planned for the later on evaluation. Now here we have also the corresponding institutional arrangement, and the Ministry of Water Resources played a leading and coordinating role, who also led to formulate the whole scheme, and the recharge water resources and the implementation also distributed to different organizations and institutions. All of them play different roles, but with a very powerful leader from the ministry. And then I will go to the evaluation part. We have done many analysis work for this part. And the first, we evaluate the river flow change after the MAR. And the river flow, all the three pilot rivers realize their continuous water flow, and the maximum of flow rate reached to a very satisfied level. And those two pictures show the whole Chua River before and MAR, before and after MAR. And these are the water cover area change. It has increased significantly before and after the MAR. This is the Chua River. And we also do the calculations to see how the groundwaters did recharge to the underground by using the water budget based on the output and input data of the pilot river, and a total of 1.3 billion cubic meter of water was transferred to the pilot river, and the 0.95 billion cubic meter was regarded to recharge to the underground. And this is the groundwater level change after the MER. And because during the recharge period, a heavy drought occurred, so the ground level did not show a very obvious rise, but with an average drop of 0.03 meters. But compared to the uninfluential area, and it appeared more steady. Is the other two pilot river. At last, I want to introduce the lesson we have learned. We summarize the costs and the benefits into 3 points respectively. The first cost is that the recharged water should be charged, so that the water receiving province need to pay for the water. So the amount of recharged water should be very carefully planned. The second cost is that the upstream reservoir would lose the profit brought by the discharge. So they always face the trade-off of the MER. The third cost is the cleanup of the recharge is usually time-consuming and costly, but it is also necessary. This will affect the process of selection of the recharge site. The benefits are very significant. The first is, of course, the ecological effect, and the second is about the capacity and the mechanism building. We established a very effective MER implementation mechanism and our dynamic recharge monitoring and evaluation system. And about the success factors, we could see that the first is the effective institutional arrangement. This ensured and very effective mechanism to promote the MER. A second is a steady water source, even in dry seasons. And in this case, is the south to north water transfer project. The third is to apply our implementation parts, just like in this case, we found our clean up, recharge, and monitoring parts. Finally, we have summarized the future challenges. The first is, of course, the increasing uncertainty was brought by the changing environment, which could cause the increase of the cost for the transfer. The second is that the many rivers and lakes that need to be recharged actually are not in very good condition. And the meantime, the cost of the pre-treatment is relatively high. So how to prioritize them is the first issue that needs to be determined. The last challenge is that the evaluation of the effect MER requires more investment on the scientific studies. And the above challenges are also the future works that we will concentrate on. So that's all my presentation. Thanks.
Thank you very much, Jan. I think we have gone over time, so I think we can maybe only take one, Tefo, if you want to, if there's anything.
Yes.
A clarifying question.
Yeah, there is. Thanks, Karen. Yeah, there are multiple questions also in the chat box, so please post them in the question and answer. And then also, Jan, you can respond to them written in a later stage. But I will put one forward. The question is, if the water is transferred from the other rivers from the south, will that not lead to negative effects in that region where it's coming from? So so the source, if you foresee any negative effects in the area where water is coming from.
Yes. So I need to answer right now. Yes.
Yeah, you can already.
Yeah. It's very sorry. I think this is actually our question on almost every people hear this presentation will have, and we also have many people in China work on this. We focus too much on the place receive the water, but neglect the maybe some negative effect on the water source places. And I cannot see that because south to north water transfer project is a very large scale water transfer project. And every year, billions of cubic meters of water were transferred, and it is I must say that it is inevitable to have no effect on the water source. But we have to notice that the water source places are usually on the places that with more water, and after careful plan and calculations, this water is very strictly limited to its water of recharge. So the water, so I think we don't see any obvious negative impact on the water source places until now, at least. But some potential effects I cannot say right now. So we need to some further study on that. That's
Thank you. Yeah, and this could of course potentially arise towards the future if water demand increases in that area as well, as you mentioned. We do have to move on. Thank you very much. We do have a number of very interesting questions still in the question and answer box. And Jan, if you would be so kind to try to respond to them on paper, written in the chat, you can do that. Then
yes, I can.
We can in the meantime continue with Kathryn. I would like to introduce then Kathryn Sorensen, our next presenter on the case study for the US.
Thank you so much for including me. I'm very happy to be here. And thank you for thinking of the Kyle Center for Water Policy at Arizona State University. First, let me say that, let me just point out where Arizona is. For those of you who are not familiar, Arizona is in the far southwestern part of the United States. We are the Grand Canyon state. We border Mexico, California, Nevada, Utah, Colorado, and New Mexico. Central Arizona is not particularly vulnerable to natural disasters. So we don't have earthquakes or tornadoes or volcanoes, no blizzards, but it is always very hot and dry here. We are a desert state. And we know that mega droughts occur in our watersheds that literally decimate civilizations. And of course, desert communities understand the value of water, and water certainty is necessary for investment and industry in our state. If we can't prove water certainty, then people will not come and industries will not come. So Central Arizona is really built to withstand drought. So the state of Arizona is entirely within the Colorado River Basin. Our sources of water include the Colorado River and then its major tributaries, groundwater, and of course, reclaimed water. The Arizona must share the Colorado River with the 7 basin states and also the Republic of Mexico. This river feeds the great cities of Denver, Las Vegas, Albuquerque, Los Angeles, San Diego, Phoenix, and Tucson. It's often called the hardest working river in the West. It also supports huge agricultural areas in the Imperial Valley in California and also in Western Arizona. About 70% of the Colorado River is actually used for agriculture. So that is a really important part of understanding the dynamics of the Colorado River. Each state, including the Republic of Mexico, are entitled to fixed amounts of water from the Colorado River each year. Let's see, next slide. So Arizona's population really did not take off until after World War II, and that is largely because we are a desert state, and it really wasn't until modern air conditioning was available that people really started to move here, and our industry really started to take off. But for many years before this time, Arizona was not making full use of all of the Colorado River water to which it is entitled. And California during this time was very happy to make use of the water that Arizona was entitled to, but was not using. And so over time, California kind of became dependent on Arizona's unused water. Arizona really viewed California's use of its water as an existential threat, because of course we all know that possession is 9/10 of the law. And I think Arizona was worried that if Arizona could not make more use of all the Colorado River water to which it was entitled, that it would never be able to get that water back from California. And so after many decades of arguments, which themselves could be a seminar, Arizona was able to partner with the federal government to build, I'm going to go back up real quick. Arizona was able to partner with the federal government to build the Central Arizona Project Canal, which is this line you see here that stretches from Western Arizona all the way into Phoenix and then down to Tucson. This is a very large transfer project costing billions of dollars. The cities of Phoenix and Tucson, the urban corridor needed the water. The farmers in Central Arizona needed the water because without this water, they were really just depleting our fossil groundwater supplies. And the federal government needed to import this water because it has various treaty and trust obligations to the many Native American tribes within Arizona. So water transfer off of the Colorado River, the main stem, into Central Arizona made a lot of sense for a lot of parties. And we were able to eventually build this canal. It's a really large canal. It delivers a very large amount of water. It pumps water 336 miles in total, and it pumps 2,400 feet in elevation. So it's a very, very large undertaking. And for the most part, a successful one. The importation of Colorado River water into Central Arizona has allowed our cities to flourish, has allowed us to recruit and entice very large industries, and has allowed our growth and our agricultural production to occur on renewable surface water supplies instead of on further depletion of groundwater supplies. But really, Arizona was, like I said, unable to make full use of all of its Colorado River supplies. And meanwhile, California was using what was left over. So the state legislature created the Arizona Water Banking Authority. And the reason for this is that even once Colorado River water was imported into central Arizona, you know, those types of large projects, large canal and pumping projects, they're quite expensive. And it turns out that the farmers were unable to afford the water that was imported because of the cost of the project. And so without the large agricultural demands, Arizona still found it very difficult to make use of all the Colorado River water that it was entitled to. And again, one of the main concerns was basically keeping this water away from California. So the state legislature created the Arizona Water Banking Authority. So the primary objective was to take Colorado River water off of the main stem, keep it away from California, and use it to recharge our fossil aquifers. And so the importation of the water kind of became, you know, there were two benefits to it, right? We can better recharge our aquifers, make sure that they're sustainable for the long term, but also keep water away from California. The water bank has been very successful. It is funded with taxpayer dollars and with a pump tax, and has raised a lot of money and used that money successfully to recharge our aquifers. The groundwater levels within central Arizona have for the most part stabilized or improved. And that is a huge achievement because, as we know, there are many fossil aquifers around the world that are in decline. This map is actually from the Kyle Center for Water Policy. It's off of a tool that we call the Arizona Water Blueprint. And I hope you all find the time to explore it. But the areas in blue are areas where groundwater levels have stabilized or improved. And those areas are mostly are the areas that benefit from the importation of water off of the main stem. And so that has been relatively successful. The red areas are where groundwater depletion of fossil aquifers continue. And those are largely areas that don't have the benefit of importation. But what is really most interesting to me about Arizona's large transfer of water and managed aquifer recharge is the impact that water transfer and managed aquifer recharge has had on the Colorado River system as a whole. The Colorado River system is over allocated, meaning that we're entitled to take more water off of the river than the river can really provide over time. Scientists are telling us that we're in a mega drought that is the worst that we have seen in 1,200 years. And scientists are telling us that because of climate change, the flows of the Colorado River will diminish by as much as 25% over time. So this is a really big challenge. Water shortage was declared for the first time ever in 2022. And we expect that there will be a more serious shortage declaration in 2023. So this is a chart of total Colorado River water use across the 7 basin states and the Republic of Mexico. The total here includes all the uses plus consumptive uses, reservoir evaporation, and estimated evapotranspiration by native vegetation. So this is all the water use that we could come up with. And there's a couple of really interesting things to notice. First, you can see as Arizona began using its entire Colorado River allocation through the Arizona Water Banking Authority, through this managed aquifer recharge, Colorado River water, total Colorado River water use surged. Second, California, which you see down here, had become accustomed to using Arizona's unused Colorado River water. And as Arizona made full use of its Colorado River water, California was forced to cut back and use significantly less water. All told, California had to cut about 20% of its Colorado River water use, which is a huge amount of water. And it took California several years to wean itself off of Arizona's water. And as is normally the case in the Western US, the farmers in California had the highest priority rights to the water. And the cities of the coast, Los Angeles and San Diego, had lower priority rights. So as California was forced to wean itself off of Colorado River water, the cities basically had to buy out the water rights of the agricultural districts. And ultimately, California agreed to water transfers from agriculture to the cities in an amount that became the largest agricultural to urban transfer in the United States. Third, the impact of this extended to the Salton Sea. The Salton Sea in Southern California is an important habitat for migratory birds. As California, and the Salton Sea is fed in part by agricultural return flows. So as water was transferred out of agriculture in Southern California into the cities of Southern California, those return flows diminished and has created problems for health as the Salton Sea has dried up. Dust blows that contains a lot of contaminants, and there's concern about the health of the lake and its impact on migratory bird populations. And then fourth, and probably most important for Arizona, the race for Arizona to use all of its Colorado River water to keep it away from California helped contribute to the over allocation of the Colorado River and sort of exacerbated that situation. And the major reservoirs of the Colorado River are now, the water levels in them are literally plummeting. Ironically, Central Arizona's right to Colorado River water is junior to that of California. So as the federal government declares these water shortages, Arizona takes those shortages before California does. And what to me is ironic about this situation is that our use of transfer and combined with managed aquifer recharge helped exacerbate this situation and makes us vulnerable to those Colorado River shortages. But on the other hand, because we took the water and stored it in local aquifers, we're ready for those water cuts. So it's sort of an interesting case where local resiliency in Arizona came at the cost of regional resiliency on the Colorado River itself.
All right, Kathryn, one more minute.
Yeah, Central Arizona's relationship with water transfers and managed aquifer recharge is complicated. Even in urbanized Central Arizona, agriculture still uses half of the Colorado River water that is imported. A few cities, Phoenix, the capital in particular, use Colorado River water directly, take it at surface water treatment plants, and then distribute it to their customers. Other cities have avoided the cost of building surface water treatment plants. They continue to pump fossil groundwater and then use the Colorado River flows to recharge that pumping. And this is another interesting example where the use of Colorado River water supplies directly avoids the use of fossil groundwater supplies and therefore protects future generations, but makes the cities more vulnerable to Colorado River shortages. Whereas those cities who continue to pump fossil groundwater are more insulated from Colorado River shortage but at the cost of future generations. So what have we learned here? Water transfers will continue because population, industrial centers, and agricultural centers, they change and evolve over time. But and humans have been moving water for thousands of years. It turns out we're actually pretty good at this. So I expect water transfers will continue. Storing surface water underground in a place where it wouldn't otherwise have flowed provides local benefits, and those benefits have been very large in Arizona. It's been a very beneficial regime for us, but it also interrupts the hydrologic cycle, and sometimes with regional consequences. Water transfer combined with managed recharge has been a benefit to Arizona, but it has also exacerbated regional challenges on the Colorado River. So looking forward in very interesting times where the Colorado River is in decline, Arizona must continue to recharge our fossil aquifers, or future generations will really pay the price. But the Colorado River flows will be less available for this purpose. So Arizona is going to need to look to some of the remaining tools to be sure that we continue to manage our aquifers responsibly for future generations. Thank you.
Thank you very much, Kathryn. Karen, I think we have time for one question, perhaps. Given the time, there are a number of questions here in the audience, two so far. Maybe I can pose one of them. You mentioned that the farmers were not able to afford the transferred water, so it was used to recharge the aquifers where you said the farmers are pumping from. And does this mean that the water was basically provided for free via the MAR scheme?
So because the farmers were not able to afford the water, the cities whose populations were booming at the time, Arizona is one of the fastest growing states in the country, the cities understood that if they stepped in and paid for that water, that they would ultimately be the beneficiaries of that water. And as we know, it's often the case that water flows uphill towards money. And so the cities were able to take on the cost of the water and secure the water rights away from the farmers. And that was a good investment for the cities.
Thank you. And then there was another question. No, there are two coming up, and please have a look at them, Kathryn, if you can, and respond to them.
I will.
There are more coming in. So, Karen, would you like to present to present the next speaker? You are still muted now.
Thank you, Tiba. Thanks for that. So yeah, we will hand over now to our last speaker for the webinar. And this is our case from Botswana. We have actually two presenters and two representatives that will be giving the case. So we have Bogadi Mathangwane, the director from DWS, Department of Water and Sanitation in Botswana. And then we have the regional manager, we have Kelly, who's a hydrogeologist also from DWS. And I believe Kelly will be giving the presentation. So over to you, Kelly. Thanks.
All right. Thank you very much, Karen and the team. My name is Kelly Gaboiphiwe. I'll be presenting to you my feasibility study at Pala Road Wellfield in Botswana. My presentation will be as follows. I'll give a brief background, objectives of the study, the methods and how we executed the study. And then I'll talk a little bit of the key findings and the assessments we did. And finally, I'll talk of the conclusions or I'll make concluding remarks of what happened and what we really found out. So I'll straight away go to the background. Botswana is a country in Southern Africa, characterized by low rainfalls of about 250 to about 400 millimeters per annum. We also have very high evaporation rates, and these have resulted in us having very limited surface waters and limited dam sites within the country. The limited dam sites as we are, or they may be exhausted as I speak. This has meant that now we have to resort to groundwater resources, which account to about 75% of the water sources in the country. As it is now, groundwater use or utilization has increased about 30%, because water use or the demand will always grow, but the water resources will remain limited as they are. So with all this now, it was important now that we have to look into integrated water resource management. We look at water losses measures, we look at water saving technologies, water reuse and recycling, which led us to come to consider MA as a tool or as a technology that we could actually use to mitigate this water scarcity that we have in Botswana. So when we look at MA, mitigation of water scarcity has always been a major driver for implementing managed aquifer recharge. This is no different for us here in Botswana. It is also a solution to augment drinking water, to restore groundwater resources. It can also be used to manage the supply-demand status quo. Sometimes it's used to utilize stormwater for industrial use, and sometimes used for water reutilization, sometimes from dewatering waters from mining activities, and sometimes balancing of seasonal peaks and lows. This may be during peak hours, peak times where you have, for example, tourists coming into your country, and then the demand automatically rises, or sometimes in drought periods where you really don't have any water and you have to find out where you get some water. So if you have some water stored in your groundwater banks, you could easily remedy the situation. When we go to the location of the study, as you can see, this is a few kilometers from the capital city, Gaborone. And then if I can use a pointer, somewhere here in the eastern part, this is where in the Limpopo Basin, this is where we have all of our major dams, and which means now we have to transfer water from this particular part of the country to the high density areas, particularly the city of Gaborone and other surrounding villages and towns. So this is why we will see that when we talk of the objective of the project, it will be mainly limited to such a situation, or probably to the north-south area, which is the major transfer scheme from the eastern part of the country to the capital of the city. So the objective of the study was to investigate the feasibility of MA at Pala Road Wellfield using borehole injection to improve groundwater sustainability, also groundwater storage, and also supplement or give additional yields. This was mainly done here to improve also the resilience of the north-south area, which is the major water supply scheme in the country. It's also to build capacity on groundwater management and artificial recharge. The project also will compare MA with other solutions of water supply and security. So when we talk to project implementation, it followed the normal implementation processes or project cycles, beginning with the inception phase, where we do reconnaissance works, and we try and map our plans on how we are going to execute the project. And as this was one of the first MA projects in the country, we needed to do a lot of field work in form of research or in form of aquifer characterization. So this involved a lot of geophysics, surface geophysics, down the hole geophysics. We also did a lot of drilling, both injection wells and monitoring wells. We also did a lot of test pumping activities. And then we did about 3 injection tests in which we successfully injected water from one part of the well field into the other part of the well field. So we were very careful here because we wanted to use the same type of waters to investigate. So in order also to be safe, we also did a full hydrochemical analysis in order to investigate the hydrochemistry of the well field. So we basically the test was basically limited to source boreholes within the well field, and then injection wells also within the well field. So from the results of the field works, we went on to do MA assessments. So our assessments were mainly limited or were very thorough, and we used some models to help us assess or determine if MA is possible, and also determine the right or the appropriate scenarios if we were to proceed with the implementation of such a MA scheme. So some of the methods or the models we used are the numerical groundwater models, the water supply safety models. To some extent also we used the geochemical model, and then we also subjected this to multi-criteria analysis to actually determine the best scenario or the best approach. So the multi-criteria analysis was basically a decision support system in this particular case. From here, we also went into the last phase of the project, which is basically MA program development, which was based on the success of these 3 phases, or the success of the injection test. So the MA program, basically here we did a lot of, entails capacity building, development of monitoring strategy and management plan, development of preliminary infrastructure design for the pilot project, because before we also go into a full MA scheme, we will need to do a pilot. And then also identification of risks and benefits and constraints. And then we also have to cost estimate the MA facility. So in this particular case, also when we are doing the evaluation, it also involves the financial evaluation. As I alluded earlier, that we are going to compare the MA scheme to other possible solutions. We are also going to compare, financially compare the MA scheme to other available options, transfer schemes, such as the Chobe Zambezi, the Lesotho Highlands scheme. So these are some of the work that we are going to do to complete the MA development program. I don't know what these guys are doing there, but anyway, so we also, that is the setup, we call it a donkey, that is the injection well. And then this is what I just described in my 4 phases. And then some of the key findings that we had from the geophysics, we managed to locate ground vertical conductors and fracture systems in the well field. These were very important in allowing successful injections into the aquifer. For the hydrochemical analysis, we also managed to identify 2 types of waters in the well field, and these 2 types of waters were all compatible with the potable water from the treatment plant and also raw water from the well fields. So it was good results. So the drilling works also managed to provide new information. It filled the gap between the Pala Road wellfield and the Chapete wellfield. So we have very good lithographic information, and we all during the field works the field works were very intensive. We did a lot of camera surveys to confirm a lot of iron incrustations, which was from medium to heavy. We also confirmed a lot of fracturing and cavities, which were very important in transmitting injection waters, both for injection and abstraction. So all in all, the field works were completed with 3 injection tests at about 20 meter cubed per hour, 40 meter cubed per hour, and 63 meter cubed per hour. And all this now meant that we had successfully proved the concept of artificial recharge in Botswana, particularly Pala Road. So this was a very huge milestone for us. So now when we go to the MA assessment, which was phase 3, I just described, we talked of the water supply safety models, and then we simulated water shortages over time, particularly from 2020 to about 2040, a period of about 20 years. We also, what we did, we made the water supply and safety model and the numerical model, groundwater numerical model feed each other. So whatever information we got from the water supply model, we input it in the numerical model and so forth. It was a continuous and lengthy cycle, but this improved our data. So finally, we went to evaluate our 3 scenarios that we had through the multi-criteria analysis, as I will show you. So the water supply safety model basically is based on the north-south carrier and also about 9 well fields that are along the north-south carrier. It is a major supply scheme from the eastern part of the country to the city of Gaborone, or to the southeast of Gaborone. So you can see that it's a stochastic and time dependent a model, and then you can see that the dams and the well fields are here, our stocks, and then what we do here, we tried to have this particular model also talk to the numerical groundwater model. So what we have here is one of the scenarios we had for the models, and you can see the blue line. The blue line is the injection. The orange line is the abstraction, and the green line is the storage. So from these results, you can see that we have episodes of abstraction, then injection, and all this now influences the storage, the aquifer storage. So it's also important to note that for the system to work properly, we really need to abstract intensively to create a reasonable cone of depression or storage. So with this particular model, we realized that with continuous injection and abstraction periods, the storage has greatly improved. So this was modeled up to 2040. So when we look at the
1 minute.
When we look at the multi-criteria analysis, we subjected our scenarios to technical, social, environmental, and economic considerations, and we weighted these particular items so that we could see which of the criteria was more resilient or was sustainable. So this is the criteria we evaluated our scenarios on. And then our scenarios were 3. We had aquifer storage and recovery at 20,000 meter cube per day, aquifer storage, transport, and recovery at 20,000 meter. And our last scenario was extensive abstraction at 40,000 meter cube per day for aquifer storage and recovery. And then we found that the technical domain for scenario 3 provided a higher water supply security. And then we also found that the social domain on all scenarios is expected to provide positive effects. And then also from the assessment, we found that still the scenario 3 at 40,000 cubic meters per day has stronger economic performance and is the most sustainable scenario evaluated in the study. Hence, we recommend that the scenario be prioritized in further studies on implementing MA, particularly maybe the pilot. So when we look at the risks also from the study, technical risks are overall expected to be low to moderate. Social risks are mainly associated with spills of contaminant. Economic risk was mainly due to interrupted or possibility of interruption or insufficient funding. And then there was also potential for competition of resource from mining activities, that is in particular in the area of study. So when we conclude my presentation, it's important to have the following notes: that proof of concept was successful, that it's possible to inject significant quantities of water into the well field. And then we had improved knowledge, hydrogeological characteristics of the well field were known and improved. And then we also established that the well field or the aquifer is very suitable for Ma. And we also established that connecting Ma well fields to the north-south provides more water security. And then Ma provides long-term sustainable use of the Pala Road well field due to less depletion of storage over time. So we also noted that it's very important that we have good legal frameworks for effective governance of groundwater, including Ma. So in this particular project, we have done a legal assessment evaluation, and we have drafted a memo that we have submitted to an ongoing project, which is review of water-related legislation. And then where we recommended that it's very important that that they consider Ma, where they will define Ma activities, they will characterize, they will talk to characteristics of the source water, and then end user of recovered water, etc., and also the environmental impacts that may arise from the particular schemes. So these are some of the things that we realized from the study. And now the last, or maybe I think this last slide, the well field has great potential for expansion. So it's basically it's two projects in one. It's managed aquifer recharge and also well field expansion. And then we had from the preliminary information of the study, we can conclude that this study provides exciting opportunities for implementing the managed aquifer recharge pilot. And then this would be the end of my presentation. I thank you very much.
Thank you very much for that, Kelly. It's very much appreciated. Do we have any quick questions? Otherwise, I think we will go straight into the panel, because we're actually running a bit late and we only have about 15 minutes, 10-15 minutes left. So Tiba, do you have anything you want to put forward now? Otherwise, I'll raise a couple of questions.
I think we can move on, and because there's a general question to all panelists and about water quality regarding emerging pollutants, but that may come up in the discussion.
Okay, great. Okay, so thanks to all the presenters. It was a really interesting coverage of these different cases from around the world. I see we can see a lot of similarities, but also quite a lot of differences because of the timing and the level of experience and the different scales that we're talking about. I guess the sort of setting in terms of water scarcity and this disparity between wet and dry areas is very common to these kind of schemes. There's some interesting aspects I would like to maybe touch on from each of the cases. I won't necessarily ask the same question to each of the panelists, but maybe from the China side, I would like to understand a little more about sort of the impacts that you're seeing, and also there was a mention regarding deep aquifers, whether they are actually being replenished as well as the shallow aquifers. And how do you see sort of the challenges going forward? I could see that possibly these rivers and partly the aquifers will be recharged over time. Do you see that there would be a situation where you kind of recover your systems, or will this be basically an ongoing situation where you will also satisfy increasing demands as you get more water transferred to these areas? So kind of talking about the demand management, and also the share between the different users. You talked a lot about the ecosystems and so on. So what are some of those, what is the thinking around the sharing between satisfying different criteria for the transferred water and the use of that water? Over to you, Jan and Lili.
Okay, I can answer, and maybe Yan can add something. Well, about your question, so your question is about challenges and focusing on the last point you mentioned, how to balance the needs. Actually, the function for the south to north water transfer project, the main function is providing water supply for the North China Plain, and also along the transfer, along the project, there's also some cities needed water from this project. So that's a main function, that is provide water supply, and also there are other functions, including for the provide some water for the ecosystem. So that's why we have the MAR. It's because like just Yan mentioned, it's because at the beginning of the water transfer project, because some local project haven't finished yet, so the water hadn't been consumed as planned. So there's the amount which can be used for the ecosystem. Like for Hebei province, the planned water supply from the from the transfer project is about 3 billion cubic meters, but at the beginning, because some local projects hasn't finished, they only consumed 10 or 15. I mean, 1 or 1.5 billion water. So there are some other amount of water entitled for this province. So we're thinking maybe we can use this water, just put this water in the rivers and restore the river system, and also recharge the groundwater. So that is the why we have this MAR at the very beginning. And I think I hope this answer your question. And also about the other challenge I want to mention. The first one is yes, that is available for the amount of available water. That is the first challenge, because normally the water project is used. It's not only for recharging groundwater. It is for providing water supply for for economic development. And because their population is increasing, and the urbanization and also agriculture development, we all need water. So how to balance these water needs. It is the first challenge. And second challenge is the regulation, because sometimes the water the water, I mean, where the region where the water come from is in dry condition. So in this way, we maybe cannot transfer too much water. But sometimes it is in wet season that we can get more water. And even for the we need to do the regulation very, efficiently and effectively. And even for the receiving water area, there might be some flood risk. So that is how we regulate. And the third challenge is how to determine when should we stop. Because with the recharging groundwater, the groundwater table rises. And for some regions, like some regions, especially the city regions, with subways, with very big buildings, we do not like groundwater rise too much. And even for some agriculture regions, something do not like we do not always like the groundwater rise too much. So what is the criteria for each region? We can say, okay, that's enough. So we need to do some investigation and scientific analysis for various regions. So hope I answered your question.
No, that's very, very interesting and right on the spot. I think that these issues of regulation and the distribution of the benefits and the water itself is becoming very critical. And maybe once you start a project, you don't necessarily think so much about it. It's like, let's just get the water here. But then all of these questions arise, and then you have to somehow come up with solutions, make sure that most people benefit, even the nature and so on, right? And also you don't get the disbenefits as you mentioned. So there's a lot of trade-offs. I think, I guess there are major benefits, but there's also, things that could be challenges. Okay, thank you so much for that, Lili. And then I will proceed to Kathryn. Thanks for your presentation as well. Possibly you're sort of ahead of the game when we're looking at the 3 cases. So there's probably a lot of experience that could be shared, not necessarily to say that you can transfer, the approaches just single-handed. You have to look at it case by case. But from my point of view, the case that you're describing is to me maybe also there's a need to look at demand management and sort of making sure that you get the most out of the water, and you reduce use during the droughts, and you also start reusing wastewater and so on. And also maybe the aspect of energy, because you mentioned that these schemes are very energy intensive. So there's this energy, food, water nexus. I'm just wondering if you have any reflections on those 2 aspects. Thanks.
Yeah, no, thanks for asking that question. And what I will say is, in general terms, Central Arizona, the cities in particular, look to demand management and conservation first, because in nearly all cases, it's less expensive to employ conservation and demand management than to engage in these large projects. The problem on the Colorado River in that case is that 70% of the water in the Colorado River is used for agriculture. So you could literally, wipe Phoenix off of the map, and it would not make a dent in the over allocation of the Colorado River, because the vast majority of the water is used for agriculture. So we always look first to conservation, but what we say is we cannot conserve our way out of this problem. It's too big. So yeah, we look to the use of reclaimed water. We have been reclaiming and reusing wastewater for approximately 50 years now. And the bulk of that actually goes to the cooling towers at the Palo Verde nuclear power plant, which is an interesting nexus between water and power. But yeah, here, like I said, desert cities understand the value of water. And so we make use of every single supply that we can get our hands on. And I think that's a really important perspective for people to have looking forward, because, you know, with climate change, we are looking at increasing water scarcity. And to the extent that you can have a portfolio of water supplies that are physically diverse and legally diverse, that is a really, really important part of resiliency. And that's what we focus on.
That makes a lot of sense. Yeah, thanks for that. Maybe we, in the sake of time, we have to go to the last panelists. And first, I would like to just hand over to Kelly, maybe for a short review of what sort of how do you see the case from Botswana sort of fitting into the larger regional scheme of things, and how are you sort of learning from other cases, and how are you collaborating on managed aquifer recharge? I know there's quite a lot of other cases now being developed, and do you see that there will be a large demand and a large interest in managed aquifer recharge going forward, and that you are also sort of paving the way with this scheme? I can also ask Mrs. Bogadi if she likes to come in this, because it's a little more of a regional question and maybe not so technical, but I'll let it up to you who would like to answer it.
Okay, no, let me answer it first. Yes, I agree. Botswana, we may say Botswana is a late bloomer regarding managed aquifer recharge, but from the recent studies that we had and from the regional studies that are around here in Southern Africa, in South Africa, and Windhoek, Namibia, we have learned that this has been very successful, and they are actually a very viable option into sustainable water supply, or putting some sort of resilience into our water supply system, and also giving us water security. So we have found that even now in the country, there has been maybe informal ways of managed aquifer recharge that has been operating within the country. An example would be dewatering from mining activities and so forth. So recently we have received formal requests from some of these mines now to seeking authorization to discharge such waters into the aquifers. So regarding the issues of conjunctive use, because in Botswana we really don't have a choice. We don't have any more dam sites in the country, so we cannot have any more surface waters. So what we should do now is conduct or augment surface waters with groundwater. And one other option of doing this sustainably is to implement mass schemes, so that you put some sort of restoration into our groundwater systems. So it's quite an important and a good venture. That's where we think we'll be going very soon. So let me give this to my director, Bogadi, to say something.
Thank you so much. Good afternoon, good people. Greetings from Botswana. I think, you know, as we are in Southern Africa, and as a community in Southern Africa, we have what we call the Southern African Development Community, or SADC in short. And that's made up of about 16 member states. In those 16 member states, we have a treaty, and what guides the development or the management of the water resources in the region is the revised SADC protocol on shared water resources. And to see to it that we operationalize, or we realize the protocol, the region has developed what we call strategic action plans, or regional strategic action plans, or RSAPs. And these are 10-year plans that span, that have different interventions of focus areas that the countries deal with. And the main aim of this RSAPs is really to make sure that we realized the implementation of the SADC treaty. At the same time, we realized we develop plans that would actually see to it that we manage, we plan, we manage, and we protect our regional water sources. And currently we are in the Regional Strategic Action Plan 5. In that plan, we have the indicative strategic development plan, which spans from 2020 to 2030. That is what, and the regional infrastructure master plan. In that, it underpins regional growth and development. And MA is one of those infrastructure projects that the region is looking to. In essence, we are trying to entrench cooperation and improve regional integration, regional governance, with respect to water resources management, and building capacity at the same time in the region, and exchange knowledge when it comes to issues such as managed aquifer recharge. So we have three main pillars that we look at when we are doing these projects or these interventions: the issues of governance and integration, the issues of infrastructure development, and last but not least, capacity building, and resource management, because whatever comes out, we need to be able to manage it sustainably for our future interventions, and to make sure that we address issues of water security across different scales, and ultimately improve resilience by people in Southern Africa. So these are some of our efforts, and we continue to fundraise such big activities, mega projects, the transfer schemes, through use of PPP, exploring PPP approaches to be able to fund such big, huge mega schemes. So that's what I can contribute. Thank you.
Thank you so much, Ms. Bogadi. This is very interesting, and I tend to agree with you that SADC has come a long way in terms of integrating water resources management across the states and sharing lessons. And actually also on the groundwater side, there is a separate dedicated institute for groundwater in SADC.
Groundwater Management Institute, yeah.
Yes, and they've been in place now for, I don't know, 5 years or more, and they're actually doing very well, and it's like a front runner in Africa. So congratulations to you. And I think I will have to now finish. We're a bit over time, but from my side, I would like to close down by thanking everyone for joining and for coming in as speakers and panelists. And it has been a pleasure to do the seminar or the webinar with you. Look forward to other opportunities. And then I'll hand over to maybe Tiba just to say also a few words, and then to Scott. Thanks so much, everyone.
Yes, thank you very much. Thank you, Karen, and congratulations on the organization of this event. Just to wrap up, that it's really nice to see these different angles, of course, of MAR in these three presentations in terms of local aquifer storage and recovery towards more regional ecosystem and river ecosystem restoration, which is a very important component of MAR. And maybe the combination of the two in the US and elsewhere, the Netherlands and so on. So it's really nice to see that, and important to realize that no matter the scale and the angle that we give, that there are plenty of solutions out there, low cost, high tech, and that we should all try to raise awareness and to continue forward with these, with this technique that has a high potential managed aquifer recharge. So thanks again, and thanks for joining, everyone.
Well, I'd like to thank everyone as well here for such a great webinar, and for people who are sticking around still here a little bit over time. But this was really, really special. I think we had a lot of different perspectives. We had a lot of different speakers. I think we got a lot covered, and I think we had a lot of information exchanged. I think this was really great. So, I'd like to reach out again and thank everybody who participated, and all my panelists. So Lili, you, the professor level senior engineer at the General Institute for Water Resources and Hydropower Planning and Design at the Ministry of Water Resources in China. Kathryn Sorensen, Director of Research and Professor of Practice at the Kyle Center for Water Policy at the Morrison Institute at the Arizona State University in Arizona. Bogadi Mathangwane, Deputy Director, Department of Water Affairs of Botswana, Kelly GIWP, didn't get that right, sorry, Hydrologist at the Senior Department of Water Sanitation of Botswana, Yan Yang, the Senior Engineer General Institute for Water Resources and Hydropower Planning and Design at the Administrative Water Resources in China there. And then our two really great moderators, Karen Volwith, Principal Researcher at the International Water Management Institution and Coordinator for GIWP in South Africa, and Tibor Strigler, Associate Professor at IHE Delft Institute for Water Education, UNESCO. You know, I really hope that everyone in the audience found everything, just the insights, the ideas, the work being done by our panel will be really useful. So I hope that this will stimulate some creativity in your own work as well in the coming weeks and months. So if the presentation is left to you interested in learning more, remember that we'll have the recording and we'll have the PowerPoints up on our website, www.iwra.org, quite soon. As well, please check out our LinkedIn webpage and follow our Twitter as well for further updates. So if you're interested in learning more about the association and becoming a member, please join us at www.iwra.org. As you know, we are a member organization, so we rely on having our members both join and to have opportunities to present webinars like this. So if you want to join one of our task forces, we have several of them. You can, this event came from our groundwater task force, which we appreciate. So you can look at our website and find out what other task forces there, maybe something that fits your interest. Everyone, we appreciate, you know, on behalf of the whole IWRA office, we really thank you for tuning in and viewing the webinar. So thank you.